Hello everyone. Today we have with us here eminent physicist Professor David Tong. Welcome, sir.
Thank you.
He works on quantum field theory and in the process touches upon various aspects of physics. So could you tell us about your research in quantum field theory and how it has made you come into contact with other aspects of physics?
Yeah, I think so. Quantum field theory is a mathematical framework in theoretical physics, and it's the mathematical framework that underlies many different areas of physics. So it was first developed by people like Feynman and Schwinger in the 1940s and 50s to understand particle physics, what happens to the world in very small distance scales. But since then, we've understood that this is the right framework to understand the way various materials work, to understand what was happening in the Big Bang, even to understand various aspects of pure mathematics and geometry. So it's really the perfect framework. If you want to be a broad physicist and understand lots of different areas of physics rather than specialize on one thing, this is really the thing to.
What motivated you to do quantum field theory?
I didn't really go into research thinking quantum field theory was the thing for me. In fact, when I first took my master's course, that's when I first heard about quantum field theory and started studying it. I had no idea what was going on. It was the hardest thing. I was totally baffled. I thought, I sort of reached the end point of what I could do in physics. And maybe actually that was what motivated me, was that the struggle that it was so hard. And then, very slowly, and by very slowly I mean over many years, I sort of slowly began to understand more and more of what quantum field theory is, and that's a process which is still going on now. And when I was doing PhD and then later postdocs, and I began to get a bigger picture of what physics was about, I just realized this was really the key to understand many different problems in physics.
So how would you describe briefly all the problems that you're working on?
So what I really do is try to understand the mathematical structure of quantum field theory. I should say, even though it's super important, we understand so little about it. And it's mathematically, it's so unbelievably hard. Mathematicians haven't been able to even define what a quantum field theory is. So in some sense, we're working with mathematics that doesn't even exist, that mathematicians haven't yet invented. And so many of the most important problems in the world come down to solving quantum field theory in some regime. So for example, there's a problem called confinement. The proton consists of 3 quarks, but you can never get the quark outside the proton. So why? Well, we don't really know. We know it's due to quantum field theory, but we don't really have a good understanding of why that is. My ambitious goal is to understand all quantum field theories and what they do. But I tend not to focus in on one problem, but try to sort of take a bigger picture. And as I said before, this often makes connections between different areas of physics that are sometimes quite surprising. And the hope is that by getting that bird's eye view, you start to understand something more.
How would you explain to a layperson our current understanding of the earliest moments of the universe? And where do you think cosmology is proceeding today?
Oh, that's a great question. So we have a theory. We have a theory called the Big Bang theory. And it's a terribly named theory because there was no Big Bang. The universe didn't start with a Big Bang. And what's more, the Big Bang theory doesn't even tell us how the universe started. So if you want to know how the universe started, there's a very simple answer, which is we just don't have the slightest clue at the moment. But we have this very successful theory, and what the Big Bang theory does is allow us to go back in time to the very earliest moments after this mysterious beginning of the universe, which we colloquially call the Big Bang. And by the very earliest moments, I mean fractions of a second after the Big Bang. So it's a theory which works extraordinarily well, just a few fractions of a second after the Big Bang. Certainly by the time you get to 2 or 3 minutes after the Big Bang, we can do detailed calculations of, for example, the amounts of different elements that we see in the universe compared to observations, just find absolute perfect agreement. So it's extremely exciting. I think the last 20 years have clearly been the golden age of cosmology, where our understanding has just increased tremendously. To give you an example, when I was an undergraduate, I was told the universe is somewhere between 7 and 20 billion years old. That was our understanding. Okay, now it's 13.8, and we're talking about decimal places. So that gives you some sense of how our understanding has improved. But we're not close to the end. There's still many questions that we'd like to answer. Not least, what is the Big Bang itself? And I hope that this is a question that's within the remit of science. How did the universe start? As I said, we haven't answered it yet, but I would certainly hope that it's something that we as humankind can eventually answer. And then lots of other hopes from experiments which are ongoing, or future experiments that are going to launch, that again can just give us some more indication of what was happening back there. So one thing we'd hope to see, let's say in the next few decades, is hints of gravitational waves from the very earliest moments of the universe. And if we could measure that, that would really be a tremendous advance in our understanding.
I've heard about quantum gravity. What is quantum geometry?
Okay, quantum geometry is actually one of these things that means slightly different, something slightly different to different people. So quantum gravity is the hope that we can combine together Einstein's theory of general relativity and quantum mechanics. And Einstein's theory of general relativity is ultimately a geometric theory. It explains gravity through the geometry of space and time. So in some sense, quantum geometry is the same as quantum gravity. But our mathematician friends also care about geometry for completely different reasons. And so they've also realized that when they're thinking about geometry, they can sort of push themselves to places where the geometry tends to evaporate, and they need to replace it by something else. And one of the wonderful things about string theory, which is perhaps our best physical theory for a theory of quantum gravity, not one that we have any experimental evidence for, but nonetheless the best theoretically developed one, is that it connects perfectly with what our mathematician friends think about. So I can give you one example. Mathematicians care about objects called manifolds. So these are geometric shapes, if you like, often in higher dimensions. And mathematicians care about how you think about different manifolds, how you classify them. And string theorists told them, this is 20 years ago now, that they'd been missing something very important. That actually two manifolds that mathematicians thought were totally unrelated to each other are basically the same when viewed through quantum geometry. So this is something called mirror symmetry, and it's been very important development in mathematics.
Wow, that's very interesting. So how did it feel to be placed in the same league as physicists like Hawking and Maxwell when awarded with the Adams Prize?
It was, obviously it was an enormous pleasure. It also feels a little bit silly, if I'm honest, because I'm not Maxwell and I'm not Hawking. You look at what Maxwell won the Adams Prize for. He won it for showing what the rings of Saturn were made of. And he did this mathematically. He showed that they couldn't be fluid. He showed that they couldn't be solid. They had to be lumps of rock because nothing else worked mathematically. Similarly, look at what Hawking won the Adams Prize for, something very deep in general relativity. You look at what I won the Adams Prize for, something tiny and insignificant. So, it's nice to win the prize. It's nice to have my research acknowledged, but to think that it puts me on anything like Maxwell or Hawking's footing is just nonsense. Said another way, they won these at the very beginning of their career, and then they won 1,000 other prizes afterwards, so this is never mentioned. This is the only thing I ever won, so this is the highlight for me.
Could you tell us a little bit about your education and the trajectory of your career that has led you to where you are today?
Yeah, I had a slightly unusual path through research. So the standard path in England is you go to one of two top universities, which is Oxford or Cambridge, and then from there you proceed. So I applied to Oxford and they didn't want me. They told me no. So I went to a university called Nottingham. It was a great university. I got a really good education. And then I went to London, and then I went to what turned out to be a great idea. It's the University of Swansea, which is in Wales. Wales is a country next to England. It's part of the United Kingdom, very small country. And I think it's fair to say that Swansea isn't one of the world's great universities, but it's a wonderful place, and it had an absolutely fantastic theoretical physics group. They'd just started the year before I arrived, and they were full of very bright young people who were determined to make an impact on the world. And so I really thrived there. I thought it was a wonderful place. So I did my PhD there. I ended up going to the University of Seattle, University of Washington in Seattle, for the end of my PhD. So I got to see a bit of the world. But then I think it was true, certainly back then, and I suspect now, if you don't start your research career from one of those top places, there's a little bit of a battle to work your way up. So after I finished my PhD, I think I applied for 120 postdoc positions, and I had one offer out of 120. And the one offer was in TIFR in Mumbai, which of course is one of the great research institutes in the world. I didn't really know that. In fact, I knew nothing about India and nothing about TIFR. I just read this book called A Suitable Boy by Vikram Seth, which is set in India, I think in the 1950s. I thought this sounded like a wonderful country. I got this offer from TIFR, so I went to Mumbai. Then I went to London for a year, then I went to New York for a year, then I went to MIT for 3 years, then I went to Stanford for a few months, and then I got this job in Cambridge, and I've now been in Cambridge for 15 years. So I had a little bit of an unusual route, but it did mean I got to see the world, and I got to visit many places, which was really wonderful.
Could you tell us about your experience living in Mumbai and working under Professor Sunilmukhi?
Yeah, it was a wonderful thing. And I'm not sure if it's the greatest thing I ever did in my life, but it may be in the top 3. Just moving to India, it was a culture shock.
Yeah.
Well, I won't lie, but I loved it. I absolutely loved it. I've come back, I don't know, 20 times since. I've lost count. TIFR in particular is a very easy place to live. There's a colony right by the campus. You live there. This balcony that looks over the Arabian Sea. It's absolutely stunning. It's very relaxed. As a Westerner coming to India for the first time, and this was in the late 90s, and India has changed greatly since then, it was a little bit daunting, just kind of finding my way, at least to begin with. But TIFR is this very easy environment, and then somebody once said, if you're in TIFR, it's a wonderful place, and you can walk to India should you want to. And I sort of felt that. So it was like, living in an enclave, but having, Bombay, which is the most exciting city in the world, I think, just right there on the doorstep to go and explore. And you asked about Sunil as well. So Sunil was one of the many physicists who was just extraordinarily kind to me, who sort of took me under his wing, showed me the ropes, and explained lots of physics to me. So I was very lucky to end up there.
What is life in Cambridge like?
Oh, it's a wonderful and very silly place. It's utterly beautiful. It's a very, very small town dominated by the university, which isn't one campus, it's spread throughout the town. And in particular by these very ancient and old colleges. The university is 800 years old. Many of the colleges are much newer. They're only 500 or 600 years old. And it's wonderful, but it's evolved over 800 years. The university has evolved. And so things perhaps don't work in the most efficient way possible. And there's all sorts of very weird quirks and oddities about the place. Having said that, the department that I'm in, which is the Department of Applied Mathematics and Theoretical Physics, this is much newer. This was only founded in the 1950s. The building we're in is just 20 years old now. And that's a place that is just like any other modern department. There's very few of these strange things about it. You don't have to wear the silly gowns and the silly hats. But the colleges, that's slightly odd.
Tell us about other traditions of the institute, other than the gowns, I mean.
So there's the grass, of course. One cannot walk on the pristine grass unless one is a fellow. Then it's allowed. Quite why they just don't make the rule that no one can walk on the grass, I don't know. But if you were to walk on the grass, they might not shoot you, but they would come very close. If you were to walk on the grass with me, this would be totally acceptable. So this I find very, very odd. I just don't walk on the grass because it doesn't feel right. In Trinity College, which is my own, there's also a wonderful tradition which was filmed in the film Chariots of Fire. So there's an enormous court, and it's huge, the court of Trinity College. And one day a year, when the clock rings 12 at midday, the challenge is to run the perimeter of the court within the chimes of the clock.
So your lecture notes are very popular among students pursuing physics today. What made you choose to make the lecture notes freely available to everyone?
Oh, it just struck me as obviously the right thing to do. Just, if you want to write textbooks to explain physics, it's clear that the right thing to do is to put them on the web page for free, and then many more people will download them. And I'm certainly not alone. There are many people around the world doing this. In fact, whenever I'm trying to teach a new course or learning a new subject, of course I look in the textbooks, but I personally find it much easier just to find what other people have written online and learn that way.
It's a great thing you're doing. Personally, I'm a person who has been helped by your notes.
Oh, I'm pleased to hear it.
Yeah.
It's what they're there for.
So what led you to science communication to the general public? What has been your experience of speaking to varied people from maybe at events like the Hay Festival or Salon London?
That's something I really just fell into. And it's one of those things where if you do one thing, things tend to escalate and spiral. I kind of enjoy it, and sometimes I'm just utterly terrified when I do it. So the Hay Festival is a big literary festival in the UK, the biggest literary festival in the UK. I think I was the only speaker who didn't have a book to sell. I'm not quite sure why I was asked to speak, to be honest. I found it a very terrifying experience, but you should just do something in life that pushes you a little bit, and pushes you outside your comfort zone.
What advice would you give to someone in the scientific community when they're trying to communicate their work to somebody outside the community?
I'm not so sure that every scientist should be trying to get their work out there, because it's such a high bar to do something well. I think my only advice is, if you enjoy it, do it, and if you don't enjoy it, do something else.
So who would you call your mentor?
I don't know. There's been so many people I've been lucky to work with. The most important was probably my PhD supervisor. His name was Nick Dory. He's actually my PhD supervisor in Swansea, but he moved to Cambridge the same time as me, so he's been my colleague for the last 18 years. He was super smart, he was super supportive, he set me on good problems, and that was, that springboard is so important for young scientists. But since then, I've just had many people I've been lucky to work with. And you don't make it in science just by sitting in an office and doing work on your own. You need to have people that are supporting you, whether that's through giving you postdoc positions or writing supportive recommendation letters for you, or collaborators who you work with. I think it's true to say all my best work has been done with collaborators who are very smart and have brought something different to the table than I could.
So what role would you say your family has played in where you are today?
Oh, they've been wonderful. I think, to begin with, certainly my extended family, my grandparents, were kind of confused about what I was doing. No one in my family had ever been to university before. Certainly no one had ever gone on and done a PhD, and they just didn't understand. They didn't understand why. Okay, you got the degree. Why are you doing a second degree? And why are you doing a third degree? And when are you going to get a real job? That was the question they would ask. But my immediate family, my mother, my father, they were very supportive and very proud. And of course, we all know that makes life very easy for you if you have a supportive family behind you.
So what are your hobbies? What do you do when you're not doing physics?
Oh, I only do physics. It's not quite true. Actually, maybe it is true. No, I like traveling. That's the other thing.
So you have been to a lot of places in the world. What is a memorable experience? Which city have you liked visiting the most?
Oh, and I'm going to sound like a broken record, but Mumbai is just a spectacular city. I mean, it's just full of so much energy and excitement. That's one that I fell in love with immediately. New York was another one, actually. I had 1 year as a postdoc in New York. I did almost no physics in that time. I was having the best time of my life.
So pick a city that you would like to visit.
I think Shanghai I've never been to. I don't know China that well at all, so Shanghai is certainly one I'd love to go to. Rio is another one that just seems utterly stunning and beautiful. Actually, one other is Calcutta.
Okay.
Because I have so many Bengali friends, and it's clear that Calcutta is something very, very special.
Is there anything you'd like to tell your 15-year-old self?
Oh, I was so full of arrogance when I was 15. I wouldn't have listened anyway. There would have been no point.
There are many students today who look up to you and your research and your work and consider you like a role model. Who would you consider was your role model?
Stephen Hawking, always, because he was the famous scientist when I was growing up, as he was for many, many years. But of course, he's such a unique human being that it's hard to sort of have him as a role model. It's not like you could be Stephen. He's just someone very special. Beyond that, I'm not really sure. I sort of I loved the Feynman lectures when I was young. I found them very inspiring. Now I read back, Surely You're Joking, and I can see they're viewed through the lens of this decade, and the Me Too movement is slightly shaky ground in some places. Yeah, I don't think there was one, but I always found physics and popular physics books very inspiring when I was young, and that was really the age of 16 or 17 when it wasn't school that was pushing me or family. It was just discovering that there was this world out there through those popular physics books that helped.
What advice would you give to a budding physicist?
I think the two most important things is work hard. It sounds obvious, but it took me a long time to realize this. The other one is have fun, because if you're working hard, you need to be having some joy out of that. And if you're not enjoying it, it's not the thing for you, and it has to be giving you this sense of fun just to keep getting up every morning and keep doing it.
So that concludes the interview. We'd like to thank you for being here and giving us this opportunity to interview you.
Thank you for having me.